very pleased to have Carol over here from the UK. She is with Sea Mammal Research Unit, SMRU, SMRU, however you want to say it. And she's going to talk about some of the animals that really are the greatest conundrum, and that is the marine mammals around tidal devices. Hey, Carol. Thank you. Welcome. Do we have to open it? Oh, good. Okay, good. All set.
Okay. So Rhiannon did a great job in doing the first part of my talk, which was basically a quick overview of particularly the tidal industry in the UK and the rapid amount of development that's happened over the last sort of 5 years. So I won't dwell on that. So this is just showing kind of where those projects are happening. We've got a number of developers and projects that have actually been deployed and are getting wet and they're operating. A combination of test centres such as at EMIC in Orkney, but also some activity down the Strand of North in Northern Ireland. There are then a next wave of projects that are coming along that have been consented but not yet deployed. A couple in Scotland, Maygen, Sound of Isla, and a couple in Wales, the Annex Skerries and the Tidal Energy Limited project in Ramsey Sound, which I'll come back to later on in the talk. And then there's an even bigger wave coming on that projects that aren't yet consented, that are in the planning stages. Rhiannon talked about the uncertainty and environmental uncertainty in getting these projects through the planning process and actually getting them deployed and generating. I think that it's probably fair to say that collision risk of marine mammals in the UK is probably the single biggest issue that's holding back the consenting of this next wave of projects. We're actually now in a position where there really isn't any environmental headroom, so to speak, to get these projects going because the uncertainties are too great. So I was going to talk you through some of the work we've been doing in the UK with some of these developers and some of the approaches we're taking and will be taking over the next few years to try and resolve those uncertainties. So collision risk for marine mammals, the approach that's been taken to date to get these projects in the water has been basically a predictive modelling approach, whereby we're looking at predicting the number of collisions that are likely to happen over a given time period. And there's two main kind of inputs into this. So what's the probability that an animal will be in the same place and time as a tidal project, tidal device? And then given that probability has occurred, what's the probability then of an actual strike taking place? Those are the two main elements that go into predicting collision risk. But of course, there's a whole bunch of data needs there. So in terms of encounter probability, what degree of sort of macro scale avoidance and attraction might be going on? What actually is describing the behaviour and the movement of animals around these areas? What's their depth distribution, and also what's the spatial and temporal distribution of them actually being there in the first place. In terms of the strike probability, at a much kind of closer range, micro-scale avoidance or evasive responses, what are the turbine characteristics and what are the animal characteristics, so things like blade size, blade speed, and also swim speed, animal body size, and animal behaviour. And then that's kind of where we're at the moment. And at the moment, the UK consenting process assumes that every collision results in mortality, which, of course, is uncertainty means that that's a sort of precautionary approach. But of course, it's not likely to be the case. So we've got the second step, which is sort of the probability of a strike resulting in mortality. And for the moment, I'm ignoring the sublethal effects, but we're just trying to refine this as we go. So the data needs kind of feeding into this, so the speed of the strike, which part of the rotor actually connected to the animal, which part of the body did that blade connect with, and what the tissue properties of that part. And those are kind of the main features to link the number of collisions to the number of deaths. And then, of course, the next step beyond that is what effect does that then actually have on the population concerned? And that's what regulators are concerned with. What's the ultimate effect on the population in most cases? And there's a whole bunch of different data needs that feed into the population consequences. What are the vital rates of that population? What are the growth rates? How healthy is that population? Is there any relationship? Are collisions random across the whole population, or are certain age groups more likely to be vulnerable? Is there a sort of density dependence acting on that population? How likely is that population to recover from an impact? Okay, so that's quite a kind of complex picture. So I'm going to talk you through some projects that we're starting to get a handle on some of these, and somewhere where we hope to get a handle in the future. Yeah, just to point out that there's a lot of these things that are relatively unknown. And because these things are unknown, in the UK that gives us a problem, because of the main legislation that drives consenting of tidal energy. But these two pieces of legislation are kind of all part of the same European directive, the Habitat Directive. And these dictate the kind of predictions and assessments that have to be made on these projects. This legislation doesn't like uncertainty. It's very difficult to get projects through these legislation requirements because of uncertainty. The onus is actually on developers to demonstrate that a project will not have a likely significant effect on these marine mammal populations or marine mammal designated sites. And of course, it's very difficult to prove a negative. So that gives us a bit of a problem in that we have this uncertainty, therefore we can't consent to many projects as we'd like to, therefore we're not really doing that learning about the risks. The approach that the UK government to date has taken has been one of adaptive management. Deploy and monitor with adaptive management. And those few small-scale projects have been consented under this policy, in that there's an exception that there is uncertainty, but these projects are small-scale enough, and there's either the right mitigation in place, or they're not in sensitive areas, to allow these projects to go forward. And then the key is actually getting the right kind of monitoring techniques and technologies in place to do that learning on these early projects to translate up to the next stage of development. So, the first project, this is effectively the world's first commercial scale tidal energy device, and you're probably all familiar with the CGen device at Stratford Loch. Because of the uncertainty, and this is actually in a SEAL SAC, so a European designated area protected for its harbour seal population. So therefore, there was no way that the government was going to let this project run without any mitigation in place. So what effectively still happens to this day is that this guy, Andrew Murray, he sits in his little office in the Marine Lab in Port Ferry, manning this underwater active sonar unit. And whenever a potential marine mammal target is spotted, effectively the red button is hit and the turbine shuts down. Originally it was an MMO on the pile here, but we progressed to using the active sonar to cover 24/7 operations. So as long as this is in place, we're not really learning about that real near-field collision risk. But having said that, we have done some work over the last 5 years that have actually given us some of that information on that wider scale behaviour information. So I'll just talk you through a couple of those. So this sort of information here we've managed to build, we're starting to build up a picture. So we've done a series of seal telemetry deployments where we've tagged seals with GPS mobile phone tags which transmit animals' locations through time and line behaviour. And so this is just a result of unfiltered tracks of animals over one of those deployments. We carried out 3 of these, one before the turbine was deployed in 2006, one during the construction period, and then another in 2010 when the turbine went operational. So if you draw an imaginary line across the site of the turbine, and that line then becomes the axis for these 3 diagrams, these show how the distribution of animal transits across this line changed in the 3 years of deployments. So before there was anything in place, most of the transits were actually in the centre of the channel. This was during the construction period, and you can see there's a degree of an avoidance starting to happen. And then when the turbine was fully operational 2 years later, there's a definite dip in transits around the position of the turbine. So potentially evidence that animals are avoiding the device. And interestingly, no evidence for a barrier effect, despite the fact that it's quite a narrow channel, and the seals are still transiting past the turbine to get to haul-out sites within the law. Using the same data set, we've managed to build a picture of animals' depth distribution in the channel around the operating turbine. And so this just shows percentage usage against the depth. And this just indicates the depth at which the turbine rotors are. So we can see that seals are actually mainly using depths below and above the rotors. So we're actually spending less time in the vicinity of the rotors than we would predict, assuming a uniform dive distribution. Now the next step for this project, we're actually in a position where, given the information that we've built up to date, and given the development of the monitoring technologies to allow us to do this, we actually have a license now to remove that mitigation and carry out a monitoring program during that to actually determine near-field interactions of seals with the turbine. Hopefully this will happen next year, and we'll get some evidence for near-field evasion or avoidance, or at the very least be able to characterise encounter rates in the vicinity of an operating turbine that isn't shutting down. So that's to feed into this area down here. There's another project coming online very, very soon where we'll actually hopefully start to collect those kind of data. And this is this Tidal Industry Limited's DeltaStream deployment in Ramsey Sound in Pembrokeshire in Wales, south-west Wales in the UK. And this is due to go in the water in a matter of weeks. I think we come back from Canada is when that's actually going to be deployed. And what we've designed and implemented for this project is a suite of passive and active acoustic monitoring of near-field behaviour of marine mammals. So we have this array of, this is a 12-channel array. Each of these clusters is 3 individual hydrophone units that will give us the ability to detect and track echolocating porpoises and dolphins in 3 dimensions around the device. And this is actually a picture of inside these tubes. And this is the marshalling enclosure in which sits all the data acquisition equipment for the passive acoustic system. And this is where the cables are actually going out of the tube to hook up to the hydrophone. So this is real, this exists. We've been talking about this in theory for the last 2-3 years, so to see this actually happening is massively exciting. And in addition to that, we've got active acoustic monitoring where we have a Tri-Tip Gemini multi-beam sonar mounted on a remote acoustic monitoring platform. There's also an ADCP in there, which is situated about 35 metres away from the turbine. It's cabled into the turbine and then to shore, so it's powered from the turbine, and the data will go back on a fibre optic cable to the shore. So watch this space. Another project I'll just mention briefly is we just started with Scottish Government funding under their demonstration strategy, which is basically to support the first movers in Scottish waters, the first small arrays that are going to be deployed. We're helping to develop and test the different sensor technologies. At the moment we're focusing on passive acoustics and active acoustics, but we're also exploring underwater video and the use of acoustic tags to track animals. They can also be picked up by the palm sensors. We're also working on developing the analytical tools. We're kind of a step behind in this, in that we're going to be collecting all this data very, very soon, but we don't really have the tools to analyse in the way in which we probably want to when it comes to it. And these will, hopefully the results of this, or the outcomes of this project, will be deployed in 2015-16 the main GEM project in Edinburgh, where harbour seals are a big conservation concern. And then I'm not going to talk too much about the rest of the stuff other than just to highlight where work is going on in these areas. So in this area, to actually focus on the consequences of collision and sort of refine that link between collisions and deaths. There is the work that was done at PNNL to strike wildlife. I understand that's been extended to other species.
We're working on Harbour seal and MCT right now. Yep.
Brilliant. There's also a bunch of work going on at Smrug where the guys are I don't know how to describe this without it sounding hilarious. Driving a boat with a turbine blade mounted on the front so that it can control the speed into dead seals. And then monitoring, taking the carcasses and looking for bone breaks, taking them, putting them through MRI, CT scans, to look to see what forces need to actually physically break skin, break bones. At the moment done with carcasses that have been frozen, and hopefully moving on to fresh carcasses. And then there's a project that's been carried out at Manchester University, which is looking at it from the other side, from the engineering perspective, i.e. what will happen to a blade when a marine mammal hits it, but it can also potentially yield some interesting information for us as well, if we're interested in the consequences for the animal. And then the last stage, the population consequences. Currently, consenting approach in the UK is using the PBR models of potential biological removals. So basic calculations done on each population to see what's the maximum number of animals that can be taken from that population and for the population still to remain sustainable. That calculation is carried out, and if the collision risk modelling comes out with a number below that threshold, great, consent with monitoring conditions. If not, then that's where we have an issue, and that's what's currently constraining the consenting in the UK. So we're kind of starting to explore other approaches for maybe slightly more refined ways of doing that. And what we're looking at is adapting a model that was developed, has its origins in the Austin Naval Research in the US for understanding the effects of acoustic disturbance, but we've been thinking about modifying it for various impacts of renewables in the UK, offshore wind and also tidal turbines. And I want to put peacock, but they wouldn't let me. Population consequences of collisions, but that's not a popular choice at the moment. But until someone else comes up with another name, I'll be calling it peacock. And then once we've kind of gone through, refined this prediction, how do we sort of prove that negative? Is there a way of verifying our predictions in terms of collisions? The monitoring approaches I've talked about, the PAM, the active acoustics, aren't going to provide data at resolution to allow us to determine whether or not these collisions are actually taking place. By the time a signal starts to show up in the population, it'll be too late. Most of these projects are in areas where you're not going to recover carcasses. How do we verify these? And I know that there's a project that Rianne has been spearheading in the UK, looking at the development of a collisionometer, looking at a range of technologies and options for actually detecting whether or not an actual strike is taking place. So if I was to summarise lessons learned from what we've done to date in the UK, I would say that firstly, site selection is important. If you can choose a site that isn't sensitive, choose that site 9 times out of 10. But I know that's not always possible, and there just happens to be a lot of really good tidal resources happening in places that are really awesome for marine life. Deploy, monitor, and monitor, and monitor. I can't say this kind of strongly enough, but de-risking at an early stage, doing the right kind of monitoring in the early projects is the key to unlocking the potential of the industry, I think. Don't be too quick to put in mitigation steps, but be prepared to do it if you have to. But learn whether you need to, and then in parallel be thinking about what those mitigation steps might be. Because the usual kind of time scale of research is that you discover there's a problem, now we'll think about mitigation, and we'll have a 3 or 4 year research project looking at it, by which point the tidal industry is gone. So I think that's quite an important point. So yeah, design and integrate the monitoring early into the projects. Retrofitting is expensive and difficult and won't give you the information that you need, but if you can work with developers and design in the monitoring, integrate with the communications and the power systems that they're already putting in for condition monitoring, those sorts of things are key. And collaboration is probably the single most important thing. The projects where we've seen success in the UK are ones that have involved collaboration between developers, regulators. So it's not a us and them situation. It's everyone get around the table. This is new to everyone. And it's not that any particular party has all the answers. So it's getting everyone together, accepting that there's uncertainty and just trying to find the best path through it all. And that's probably it for me. Thank you.
Questions, or you can grab Carol. Great. Go ahead, Graham.
Carol, one of the things that I noticed missing is any indication of this research going on into the potential for deterrence. I mean, it's something that we've been talking about, this whole issue. We need really to have some research going on to find out, are there ways in which we can send a signal that says to a mammal, this is not a place to come to.
Yeah, and that's exactly what I meant with point about, think about what the mitigation might be and have that prepared. In the UK, I've had quite little success in getting people on board with that idea, because until they see it's an issue, the investment just isn't there. And I guess that there's so little, the research funding is few and far between, that people are really focusing on what they see as the priorities, and there's not really an awful lot of money left to look at with the mitigation steps.
There's actually been a project on the U.S. West Coast that the Department of Energy funded to try to keep gray whales, migrating gray whales, away from tidal devices that, sort of mixed success. The problem we have in the U.S., which may not be true elsewhere, as soon as you start deterring marine mammals with sound, you are harassing them.
Exactly.
So it's quite a vicious circle trying to get to that. But I think these things, as Carol says, we need to think about them, and we need to have all the options out on the table. Yeah, go ahead.
Just a quick question. I can totally see your point about not mitigating too early because you lose that opportunity. But how do you rectify this within the approvals process, where it's right, we've got our best going for the duty to mitigate it, and that's kind of the format that we've got just now?
Yeah, I think it's adaptive management. It's having the right monitoring in place to detect the issue if it becomes an issue. And that's why consenting the small projects with the right amount of headroom in an area where the population maybe isn't quite so sensitive. And it might sound quite callous, but there is an allowable mortality or no. You know what I mean?
We call it a take.
Yes, yes. So doing it in those areas where there are lots of animals around, not necessarily part of tested populations. There's a few places in the west coast of Scotland that would be perfect to do the learning. Yeah.
Lisa, one last question.
I guess one question is when you're looking at the CGen and developing the probabilities, you're looking at one device. So you did see that they were avoiding the device, but then if you have more than one turbine in there, you might then start creating a barrier, or and that would also then have impacts on the population. Is there any work going on?
There are plans to do that with the first arrays, to do similar sort of tracking studies to look at how that affects. In different environments as well. Strike is a very particular geography, where there's actually a strong motivation for the animals to get into the lock. Whereas there might be other areas where they're more open, that we might find different things happening, more of a wide scale avoidance.
Yeah, I guess because then you can then also have population effects if they're avoiding an area that's important to them.
Yeah.
Wonderful.
How close are the seals getting before they're doing a shutdown?
30 meters.
30.
It started off at 200, and then it's kind of gradually come down. The turbine can stop really, really quickly.
Okay.
So it's, yeah.
Very technology dependent, yeah. Carol, thank you very much.
Okay, thanks, Carol. That was great, and kind of in lots of ways good lead into some of the things I'm going to talk about. Focused on a specific site in the Bay of Fundy, so bringing it a little closer to our backyard right here. A lot of the things I'm going to talk about, work conducted with colleagues like the Sea Mammal Research Unit, but also with lots of my students. One of my students in the room now, so I'm going to be showing some of her slides, and hope she has some mic. And lots of people involved. I'm not going to go through all of that, but you can see that it just takes quite a bit of effort to actually do this sort of work. So here's Force, as most of you know, located here in the Minas Passage of the Bay of Fundy. It looks like a narrow place, but it is not. It's about 6 kilometers across, so it's a huge water body, and about 14 billion tons of water go in and out of that narrow opening twice a day on a spring tide. It's about, I think, about 9 billion on an eve tide. So really quite a dramatic place in there. And here you can see that all of that and that constriction actually result in a very high power density, and the reason why Force, the test center, is located in this spot. Here is a figure from Richard Karsten showing the location of the Force Test Center. Don't worry about these dots, he's referred to something else you'll see in a minute. But you can see that the Forest Test Center is located in the northern end of the passage, which is important to remember, not in the middle of the passage. The depths in here, this is multi-beam bathymetry work that was done, really about 40 to 60 meters or so. And the Forest Test Center was located here for good reason. They need to be as close to shore as possible. The cable costs a huge amount of money, and I don't know if any of you saw the paper today, but big announcement for Forest. Got all 4 of our electrical cables in this week, and it's a major achievement. It's been 5 years I've been sitting on the board of Forest, and I think those people have been sitting on the board for a really long time. I was feeling a lot of pride. Anyway, a number of other articles out as well, and some discussion about fish. And one of my colleagues here at the university is a fisheries biologist who happened to work on fish mortality associated with the Annapolis Royal Turbine back in the 80s and 90s, and is making some noise that every turbine is the same. All turbines kill fish, and he doesn't believe that in-stream turbines are safe at all, or that are going to really have much of an impact. Had my husband make this up this morning. It's just a little figure I'll just put out here. This is something I'm sort of thinking about pass around. That is a 2-scale cross-section of the Minas Passage. So the maximum depth is about 150 or so meters, and you stretch it all out with the 6 kilometers across. Look very carefully, see if you can find a tiny little red dot. That tiny little red dot is where an open hydro turbine would be and how much space it would take up of that passage, just for perspective. Anyway, what did I do with my thing? I put it down. There you go. Anyway, I think it's always important to remember when you're thinking about turbines that are huge, as big as your house, the environment that they're going in, and it's all relative, I guess. So here's the Forest Test Center here with the 4 berth areas. These are 200-meter diameter berth areas, and 1 or more turbines would go in there. So I would assume small arrays could fit inside there. And these are the cables that were just recently laid. This cable across the top, that's a data cable that was put in, and on the end of that data cable will be going a sensor platform to actually monitor the environment, and that's meant to actually happen this fall. So it would be good because we would get some very good overwinter data. So it's about 1 kilometer this way and 1.6 kilometers that way, and only large commercial sort of turbine devices are meant to go in this site. This is the lineup of technologies at present, with open hydro being the one to go in next year. I believe a 16-meter diameter turbine is still on the cards for next year. So in terms of environmental implications for this area, in 2009, when Forest became established, they were asked by the Department of Environment to form an Environmental Monitoring Advisory Committee that was set up immediately. A number of people in the room actually sit on that committee, others members or observers. That functions to help provide independent advice to Forest on its environmental monitoring program, and they also review reports that come into Forest and so forth. And with the specific interest being on the near to midfield sort of effects and monitoring within that Forest area. So Forest is responsible for looking after the monitoring that's associated with the entire test site in a general manner, and it's the expectation that the developers are responsible for the monitoring that would happen within their selected berth area. And of course, not too surprisingly, the big issues of concern that keep coming up are potential impacts on marine mammals and impacts on fish and lobsters. There's a lobster fishery in that area. There's also a herring fishers through intertidal weirs, major herring fishery out in this area here. So the big issue around this site is that it's a migratory corridor for many fish that actually come into the Bay of Fundy here, into the Minas Basin to feed in the summertime. And of course, there are lots of other fishes that are resident in the area as well. And some of these fishes are transboundary. They're coming up the U.S. coast and moving in there and going back out, so there's some issues there. and several of them are threatened or endangered. And of course, these are the ones that DFO is most concerned about because they are concerned with commercial fishes and those that have some sort of status of at risk. And this is an intertidal weir, an example of one. We have very expansive mudflats in this area, and so these get put out about 1 kilometer from shore. And actually, these can be quite long, about 1 kilometer or so in total length, actually quite effective at capturing fishes on the ebb tide. So, what have we done? We needed to actually determine what these fish were doing. We had very little data. We knew what fish were around, but had very little data on their movements, and no idea of whether or not they were utilizing the forced test area in any significant way that we need to be concerned. So we chose 4 species to look at over a 1 to 2 year period. Atlantic sturgeon at the top, striped bass. Atlantic sturgeon are threatened. Striped bass are recently been listed as endangered, not because they're low in number, but because there's only one spawning river left in all of the Bay of Fundy. We've lost two of the 3. They're actually fairly big numbers, but they're considered endangered because of that one river. American eel here, and these are salmon smolt. We also tracked lobster in this area because the fishers were very concerned about lobsters moving in and out through the forced test area. And I'm not going to show data on that, but yes, we did confirm that the lobsters do move in and out, and they go right over that sort of that shallow area on that north end. However, they don't appear to all migrate out, as the fishers initially said. It looks like there's quite a large resident population that stays in the Minas Basin, and in interviews that we followed up with the fishers, they admitted that yes, they thought that they did overwinter, and that only some of them did migrate out. So good to actually do those interviews. So we actually tagged quite a few fish, 286 fish tags. And of course, the size of the tag is going to limit, how big a battery you can have and how long those batteries last. We have some data which I'll show you where we had a longer life tags, and we actually have some winter data. So can you guys see that okay from where you are? Do you need to come down maybe a little? So we set up receiver arrays. We set up receiver arrays. We're using NUMCO technology, transmitters, sending out ping sequences that were picked up by receivers like this. And we house those receivers with acoustic releases in the sub-buoy units that were moored at 300 to 400 meter distances, just a couple, 2-3 meters above the bottom at all of these places across the Minas Passage. Again, it's the forced test site. And so basically we set this up so that we have some listening gates so that we could actually look to see, our fish moving back here. Could we get some travel rates out of this? When were they moving? Where in the passage were they found most often? What sort of depths were these fish swimming at? In our very first year, we struggled to get all of our receivers back from this line, and that was because we had some dead batteries for our acoustic releases, and we were delayed getting these receivers back in. So we made a decision that we would actually focus on the forest test site in that second year, because that was really what we were interested in, keeping this one listening gate in, which was actually a listening gate out of the ocean tracking network. So in the second year, we focused in here. One of the things about these high-flow sites is they're very acoustically noisy, and so there are some issues about any acoustic device being able to work properly under the extreme flows, because as faster the water's moving, the more noise there is, the more likely that your detection device is not going to be very helpful. And this is true this area. So what we have here on the top is we have current speed. This is the flood. This is slack water, plus or minus 1 meter per second, coming into the ebb and so forth. And what you can see is that when we actually have detections on our receivers, and these are detections of tags that are placed in very discrete place, so there's no movement of the tag. You can see that we have detections only during periods of time when flow is around less than 1 meter per second. So this is a limitation. We don't ever get a full data set like this. We only get a partial data set, but it's still providing us some interesting information that we wouldn't otherwise have. Does that make sense, this graph? Okay, so these ones are just talking a little bit more about, I think if you're going to use any instrument, and Carol would agree with me, you've got to understand how it works. And if you don't understand the limitations of what that is, it's very, you're going to have some trouble interpreting that data. This actually shows a cumulative frequency of the current speed. And here we're talking about depth average current speed, because we don't know really where these fish are in the water column. We use a depth average current speed. And what you can see is that for more than 25% of the time, average current speed is greater than 2 meters per second, which means it's really very, very fast in the top half of the water column. It's obviously much lower in the lower half. And only for about 30% of the time less than 1 meter per second. This is in keeping with about 40% of our detections are at about less than 1.5 meters per second. This figure just shows you with our range testing that with current speed this way and proportion of detections of a range test that was sending out signals on a regular basis, we have fairly high detection at slack water, but as you increase current speed, you're seeing a decline in all of that. But something interesting going on the ebb tide. So we're not getting the same sort of results on an ebb and a flood. And that's because on the flood tide, there's a lot more turbulence, and it's caused by an eddy that's created on the south shore. And even under the exact same current speed, say 2 meters per second, it's a noisier environment and interfering with detections. This one here just shows you the number of detections we had for striped bass in 2011 relative to current speed, and what you can see, obviously, most of our detections are, under 1 meter per second current speed. Flood and ebb about the same, but as you increase the current speed, you can see that most of the detections are actually on that ebb tide, even at the same modeled depth average current speed. So you might look at this, if you didn't know about this, you might say, oh, fish just aren't there. Fish, don't hang out in this area, but you can't make that claim. What we're seeing here is that this reflects detection efficiency of the instrumentation, and that's important for regulators and for industry people to know. This is a summary of our fish use of the Minas Passage. We have these 4 different fish species that I was telling you about, and some sort of summary results of that. Our Atlantic salmon, our post-smolts, were leaving the system. We have very few Atlantic salmon left. They're seriously endangered in the Bay of Fundy, and so this little project was to actually try to get some information on how they move out. So just over a couple of weeks, our tagged fish moved through the Minas Passage. Only in a couple of instances did they not make it out, and they returned, came back, and tried again. So if they arrived in the Minas Passage as the tide was turning, started to come flood, they came back and then went out on the next ebb tide. So, and the same with eels. Eels did that as well. And eels moving out at nighttime, starting to move pretty fast. 3 meters per second is going at a pretty good clip for these. So very few multiple passes. And what I mean by multiple passes is going back and forth with, in the passage, utilizing it that way. We have no data on depth distribution for Atlantic salmon because those salmon smolt are very small, and we couldn't put large enough tags in them to actually cut that data as well. American eel in the sort of top 30 meters or so. Atlantic sturgeon largely 15 to 35 meters found throughout the Minas Passage. Some back and forth movement. So they hang out in our system from spring, summer, and fall. But mostly we find them in the passage when they're migrating in and migrating out. And actually during the cable operations this last week, I was talking to the manager for us, and he asked me if we have tuna in our waters because he saw tuna jumping out of the water. And I said, no, I don't think that'd be tuna. That's Atlantic sturgeon leaving there. They're actually on their way out of the system now. So he was seeing tuna, or Atlantic sturgeon, which I was really happy about because I need him to identify with these sorts of projects. With all of these studies, the one species that probably poses the biggest concern is striped bass, and so most of my presentation really on that. They're there nearly all year round, as it turns out, which was a big surprise to us. We didn't expect that. We expected with all these fish that they would just be using the passage very intermittently and for only directed movements, you know, in and out. This is not the case. We've got them clocked at about 4 meters per second. That's very fast. That's much, much faster than you know, their normal swim speed. So they're traveling very fast. They're using the flows as well as swimming in it. So they're going at a good clip during, you know, at high speed. And in terms of going back and forth in the system, this was very common. Normally we see them at 15 to 35 meters with a bit of vertical migration to surface waters at nighttime in about the 15 and lower during the day. This is all came out in all these species, different chapters in a report earlier this year. And Donald Humphrey has a copy of it down at the back if anybody's interested in looking at it. Just want to show this one. This is striped bass, and this is the cross section of the Minas Passage. So this is the north side of the passage. So you can see it gets deeper in the middle, comes back up here. This is the south side of the passage. Force would be located in about this area here. And what we have here down at the bottom, same. These are all of our stations, our receiver stations here, north to south. And this is an abundance detection abundance graph, and you can see that. You know, on the north side where force is located, we actually have relatively low abundances. You get into a little bit deeper water. What we're seeing here is that in the middle of the passage where we have most of our detections of striped bass, it is the same for sturgeon. Most of the sturgeon detections we have in deeper water as well. So they tend to be out there. Not to say they're not here, because they're definitely in and around the force test site too, but in terms of relative proportion, most of them here. This one here is interesting, very, very deep here, so there could be something about how that receiver was positioned in some sort of, you know, very low area of the passage. It may not have been functioning perfectly if it was right in that spot. At the top here we have depths, and these are two different groups. We have a spawner group from the river, the spawning river that I mentioned, and we also have some other summer migrants which were tagged on the shores of the Minas Basin. You can see that the patterns are very similar in terms of depth. This one's a little odd, however it represents very few fish, as you can see from the abundance down here. See that? What do you think that is? I'll do it again. Yes. So if you scale this, this is scaled this so that it was, and that's why I put that little piece of paper out on your desk. This is not in proportion, obviously. This is only 150 meters. That's like 5-6 kilometers across. So if you scale this down, that would be the area of use of a 16-meter diameter open hydro turbine. So it puts it in perspective of what that is in terms of how much space it's actually taken up. So if I could stretch that out to 6 kilometers, it would be a round turbine. It's not. It's about 16-meter diameter, so I've got it focused like that. So just to keep that in mind. I mentioned before there are some vertical migrations, so we have during the daytime in and around, say, 25 to 40 meters or so, rising up to less than 20 meters at night. Interestingly, we didn't see any difference on the ebb and the flood in terms of the depths that they utilized. These are depths of concern in an area where, particularly during the daytime in an area for the open hydro turbine at least, it's just going to be sitting closer to the bottom than some of the others. But now we have turbine designs that range from being closer to the surface to being in mid-range to being at the bottom. So right now we have developers looking at all parts of the water column, not just the bottom 20 meters or so. This is some work, Freya's work, that I had her look at crossings going back and forth. And in one day, this one fish, about 70 centimeters long, went back and forth and was detected on these receivers in just 24 hours. And this is Force Test Center right there. And another fish was picked up over 103 days. And these are all the various detections, the receivers that were detected on. And this is only a partial data set because we know we don't have everything. We know the detection range is short and decreases as well as current speed gets up. So this is actually a lot of detections, given that we have you know, a small subset of what really is out there. So we know they utilize the whole passage. However, what we also know is they tend to be sort of concentrated here in the middle of the passage. We find them here in the north end of the passage, and you see lots of bubbles there, but that's because we had lots of receivers in there. We didn't put any receivers in this area here, but if you look at this one OTN line here, you'll notice that most of the detections are again, sort of in the middle. This figure here is really exciting and important to us. We're trying to get this work out pretty soon. And this actually looks at winter detections in force. And we had about, was it 17 tags? How many tags do we have? 17 tags that had batteries in them that lasted throughout the winter. And we didn't actually expect to get any winter detections. We left our devices in over winter because we started to have very good success with our deployments. We thought, okay, it's safe to leave them in for the winter. And these 1, 2, 3, 4, 5 fish here were all detected in and around force throughout the winter. So from January to April, they were out there, which was really very shocking, given that striped bass stopped feeding, at about, say, below 9 degrees C, and it's 9 degrees C over here in December, and we're getting into about 0 to 3 degrees C with ice cover in the month of February or so. So, which raised some concerns for me with regards to how these striped bass that are not feeding and maybe out there in a bit of a state of sleepiness or maybe a bit torpid, and not necessarily being able to react to structures in the water in the same way as they would in the summer season. So these are things that we're uncertain about, raises some concerns. So we're going to follow up with a bit of work this winter, also looking to see if these animals have antifreeze proteins and look at their responsiveness in the wintertime. This is an issue that I don't think anybody else has been bringing up, and none of the tests that have been done in labs to look at how they deal with turbines and throw them down a chute. They haven't addressed the temperature issue. So we know they're there, so we're going to give this some examinations. It may mean that the encounter and collision probabilities are much higher in the wintertime than they would be at any other time. And of course, it's a nice little video that Freya did, just showing some movements. This is just the month of March. The sorts of receivers picked up here, different days, same fish. We also done some work on Harbour Porpoise with the Sea Mammal Research Unit with Tom Tollitz and Jason Woods, which has been great. We did that over 2 or 3 years. And I use the sea pods here located at various sites relative to force. The presence of Harbour Porpoise is much lower here at this site than it is at most all the other tidal energy test sites, which is interesting and it's good news for a developer that we tend to have low abundance of marine mammals in general, with Harbour Porpoise, which are relatively shy, being, not liking construction zones very much, being the dominant marine mammal in this area. We have seasonal peaks during times when fish are moving in and out, particularly schooling fish like herring. So we see those peaks following the prey. Again, detection limitations in the same way. Ambient noise is a problem. The flood's noisier than the ebb tides. Spring tides are faster, so much noisier than during neap tides. And of course, we have some side effects. There's a little island over here that generate a lot of turbulence, and we get virtually no data from a sea pod that was deployed relatively close to it. So we learned from that and stopped monitoring there. And the cable guys, the guys who've been putting cables out for force, learned about it too, and nobody's going to that side of the island to do anything. Again, we use these subbuoys to mount our instruments. We also played around with this instrument here. It's an Ocean Sonics. I see this in high-frequency hydrophone. So we use them in the buoys, as well as this summer we had a collaborative project with Fisheries and Oceans and Ocean Sonics, and we put down this little platform. You can see these two units. One has a shroud, the other doesn't. So we were testing the efficiency and the detection performance of a device like that with and without one of these shrouds. We also coupled it with sea pods, and you can see here we've got fish detection receivers as well. That data is being processed right now. Some really nice data is coming off of that. So we're pretty happy about that project. This is just a quick slide on FORCE. FORCE has sensor platforms. It is building a rather large one that they're calling the Fundy Applied Sensor Technology Platform. Did I get it right? They have sort of changed the name a couple times. And the other one is sort of a mini lander that's going to be cabled to shore, and various instruments put on and off. So this is really some testing of sensor compatibility with the intention that our learnings from these platforms will help the turbine developers with attaching instruments to their turbines. So lots of collaboration potential there. This is my last slide, and I put this up because of the relevance to the regulatory issues here. I actually put this together when I was at an engineering conference in June. I was asked to speak at an engineering conference. God knows why. I don't know anything about engineering, and I was freaking. And I saw one talk, and I went back to my hotel, and I started thinking about ways to actually pull some of this stuff together. And really there's two things that are going on here. We need research and development that leads to commercialization if it's going to be sustainable for turbine developers and for this industry. But at the same time, we need regulatory approval and acceptance, and some things need to happen along the way. And really, we've been down here in order to get an industry with social license. We've been down here with the environmental baseline studies now for a few years, and we're just starting to get into this area here of sensor performance testing and advances in sensors and platforms. The OERA has a call out with the TSB in the UK to actually start working in this area so we can get over here, so we can get to environmental effects monitoring programs. We can get to best practices and standards around this type of thing, and ultimately deal with adaptive monitoring and mitigation issues, have open access to environmental data, which leads to social license, and then all along the way end up with advances in turbine technology, but also advances in data management. There's some issues about collecting a lot of sensor data around how do we process this huge volume of data. Easy to collect it, so easy to collect it, it's just too funny. Dealing with it on the other side is a nightmare. So we need a lot of this to be happening. Processing, integration, visualization, mapping, all of those sorts of things. So this is where we need to get to. This is where we've been. This is where the OERA and the TSB is trying to take us. So, thanks.
So questions for Anna?
Yes.
Yeah, thanks for that. That was really, really interesting work. So I'm excited to read your paper here. I'm just curious with the limitations that were presented for this type of technology, this type of environment. Do you see that this technology could work after the, in monitoring effects or changes in behavior of these animals once the turbine goes in? Do you think that?
I think the sort of technology we're using here does not get to behavior. It really gets to their presence and when they're there, and can direct us to some of those species. For instance, all species are not the same with regards to their use. So it's one of the questions you had: how transferable is some of this information? Some species more. So we're learning about things, and we're going to have to use combinations of technologies. This sort of work has given us sort of a mid-range scale of use of the passage, but we need to get closer to the turbine. We need to actually have sensors that operate within 10 meters, 20 meters, that sort of range, to actually look at how marine life detects and then avoids. They move around, and it sounds like some great progress is being made in the UK in looking at that type of thing. For us, our issues are around fish, and they're a lot smaller, so they're probably going to be a lot harder to detect. And it's also extremely noisy environment. It's an extreme environment relative to almost all the others.
you're going to hear a talk by Gail Zalewski in a little bit that gets at what happens after a turbine is in place. How do you look at the fish movement close to the turbine?
Yeah. They've used DITS and they've used acoustic cameras.
So next, Gail Zalewski with the University of Maine is going to talk to us about the work they've been doing around a turbine down in the Gulf of Maine, just a little south of here. So Gail, take it away.
Okay. Good morning, everyone. I'm sorry I'm keeping you from lunch, but I'll get going here. So I'll be talking about effects monitoring near an ORPC turbine, and really what I'm going to do is take kind of a broad perspective on as Anna asked me to do, is to talk about the story of how our work kind of came together. And as I have listed here, I'm from the University of Maine School of Marine Sciences, but we've worked very closely with Ocean Renewable Power Company as well as the regulators in our area to do the research that I'll talk with you about. And I won't get into a lot of the details of that research. I'm happy to talk about it when we get into discussion later, but I can do that. And I kind of throw this slide up here because it's an intriguing new development in our work that I won't really have much time to talk about. But this is an echogram of two of the ORPC devices that we've been trying to do some monitoring around in terms of fish interactions with them. So moving in, I was kind of trying to get a handle on what to talk about today, and Andrea and Anna kind of put out these several questions about the people in the room and what you're thinking about moving forward for tidal power development, particularly in Canada. And so what I thought I'd do is kind of give you my perspective as a scientist working in this arena and kind of talk about some of the regulator questions that came up as we were doing our research, how we interacted with the developer, ORPC, and what information they supplied and what we were able to provide from the scientific perspective as we were developing questions with them in this regard. And really, I really want to come back to and focus a lot on relationship building, and it's really great that you're all in a room together because that's the beginning of how all of this really comes together. So I will come back to that throughout what I'm going to talk about today. But really, the things that you want to do are define the questions, and you've talked about a few of them already, but some of the questions that I noticed are in your list for discussion in the areas of special concern for the regulators, and some of the discussion that's already happened are looking at collision and evasion of marine animals with devices, and then there were a couple other that were mixed in there, effects of underwater sounds and EMF. But I'll talk about some of our work that's helping us move towards an understanding of collision and evasion for fishes. So our work started, as I said, I'm at the University of Maine in the School of Marine Sciences, and ORPC identified a problem as the industry partner. They came to the university, I would say back in 2007 or 8, and said, you know, we know that there's going to be some kind of interactions. And this was before we had a very good regulatory process in place in terms of how would we handle what are the potential interactions of marine animals with devices. So we started talking about different approaches to answer those questions, and we quickly, between us and the industry, sat down with the regulators who we knew would be needing certain information to make decisions about putting a device in the water. And as I've already indicated, there has been a device in the water, so our work has worked to that point where the ORPC does have a license. But so really the beginning of our work was how do we define this problem together, and what information does everybody need to answer the questions that are out there? And I'll get into some of the specifics. But the other thing I wanted to bring up is this has been an iterative process where we've started implementing our research, compiling results, and then working with the regulators again to communicate those results and refine the needs and then go around this again. One of the things I want to point out, and I won't get into detail, but a lot of our work has also involved fishermen in the area. Realistically, these areas are very difficult to work in, and fishermen have become an important piece of this mix as well. And I won't have a chance to talk about that, but wanted to mention it. So really, one of the things that I wanted to bring up and come back to, and is all related to this idea of relationships, is it maybe seems simple right now to say, okay, what are the questions that we have? But really, we need to consider how those questions might change, because as I showed you that loop earlier, that loop continues and is iterative over time. So I think that one of the big things to think about is flexibility and communication. And again, being in the room together is one of the biggest things that kind of helps get over those some of the issues. So in our case, I wanted to give you the ORPC main example. As I mentioned earlier, one of the first questions was, what will happen? And we've come a long way since then, and I'll show you some of that. But really, the initial questions are, how will essential fish habitat be affected? What are the laws that are under consideration by the regulators? And what information are needed to answer those questions? And then on the scientific side, and hopefully you'll get into this a little bit more, what can we assess? What is even possible? What is reality? And then as we were going around that loop that I mentioned earlier, the questions start coming up. Are we asking the right questions? And this is where the flexibility and communication are very important, where all of these questions are defined collectively and help move projects forward. So I wanted to get into this idea of, or kind of move towards this idea of asking the questions about how do you assess animal device encounters, and what have we been doing to think about collision, evasion, and potentially attraction. And the diagram on the top of the slide there kind of just summarizes the potential effects that can be really wide-ranging in scale and duration, and kind of our visualization of what that is starting to look like. And I think that Carol mentioned earlier some of the ideas of, what are the vital rates that we need to understand, what are the probabilities of mortality and strike. And I'm not going to get into a lot of the specific details there, but give you some ideas of where we're heading for fish, which is, as Anna said, a slightly more complicated, or it's a difficult problem because the diversity of fish that are out there and the life stages that you're dealing with over time are very different, vary a lot. So we've been thinking about this from the standpoint, and this has already been brought up again, that fish abundance and vertical distribution affect their likelihood of encountering a turbine. So over a long period of time, we've been thinking about what is the distribution of fish in the water column, and how might that affect the rate of encounter with the device. And so the next diagram you see here is, is that affect, are the animals avoiding or evading right at the turbines? Are they avoiding at some intermediate level? Are they avoiding much further away? And of course, this could be related to various different life history variables or life history stages and sizes of fish. So our first question started at the device, because the first question that everybody wants to know are these devices directly impacting individuals? And so our work started in Acoustic Bay. This just gives you a perspective of where we are in Maine. And this is the complexity and what Acoustic Bay actually looks like. And the bottom support frame of the ORPC turbine is shown in the bottom right-hand corner there. I'm assuming you're all hearing me and I'm not just going on and disconnected.
Sounds great, Dale.
Okay. Because I'm hearing nothing, so it's disconcerting from this end. Okay, so I'm going to continue. So our first work, as I mentioned, was to look at direct interactions with the device, and ORPC had a test turbine that they had on this research platform shown on the lower left that we took advantage of to try to start getting an idea of what actually happens when a fish might be encountering a device. And so we looked at within 5 meters of a device, what do fish do? And we started quantifying and collecting empirical data on what the fish are doing as they're approaching or departing that device. So the depiction on the right is the turning turbine, horizontal turbine, and from the side, looking from the side, and the flow is going from left to right in the diagram. And what we did is, over a period of time, we collected data on, numbers of fish that we saw in different parts of the view that we had. And we can get into the details of how we collected the data later. But essentially what we saw is that slightly more than half of the fish that we saw were already moving above or below the device. So they potentially could have evaded the device previously to being in the view of our images. We had, of those that we did see at the level of the device, 48% of them actually went in, and then we saw some come out as well. And then we did see active avoidance. So of those in that area, only 1% actually actively avoided the turbine and were able to move above it or below it. Now, with all that said, I'm simplifying, obviously, this very much. And there are caveats to be had here where thinking about fish size, whether or not the turbine was turning or not, because it doesn't turn on the slack tide, affected the behavior of fish, whether the fish were large or small, again, whether they were there during the day or at night, and whether the turbine was turning or not. So there are definitely different effects during those different periods of time, which need to be considered when you're thinking about interactions with the turbine. So our question became, though, what happened to these fish that just passed by? Where was it that they were actually able to show a behavioral response previous to the view of our cameras? So we've also been conducting some longer-term studies to look at using acoustics to look at vertical distributions of fish at the site where the turbine would be or it was located versus a site that's further away. And really what we're trying to get at is what is the probability of a fish being in a certain part of the water column and then potentially encountering the device. So again, knowing where they are in the water column, knowing where the turbine is, you can generate probabilities for different depths of the water column of whether or not you think fish would be interacting or encountering a device, if you knew where the behavior change would occur. So I'm not saying I have the answers to all of these questions. We're still working towards a lot of that. But what we have been doing is working towards a probability of encounter model where we know, from some of our work, we have an idea of what happens near field to the device. So for the smaller fish that we saw there, only 1% of those fish are actually able to avoid. So in that near field, we have a probability of what happens to the fish. But our questions are now, as you move further away, where are they potentially avoiding the device? So from some of the data we've collected over time, we're starting to develop an idea of what is the proportion of fish that use that depth of the water column generally in that bay. And then as you get closer, where is it that we might start seeing behavior change occurring? And so we're right now building this data set. We've actually collected data over this last summer around the Ocean Renewable Power Company Oxgen, which is not the device shown here. And we're building this model to try to understand where is it that evasion might occur for these fish. That said, and so that's kind of the data part of what I wanted to tell you about. I wanted to come back to the idea of working in a difficult environment, and Anna already kind of covered this a little bit. But, we're not doing the standard towing in these environments, and it's simply because the picture shown on the bottom right is the topography that a lot of us or some of us are dealing with. This is the topography in an area right near a site that's of interest for tidal power development. You're obviously not going to tow a net through that area. And the top picture there is the Old Sow, which is a large whirlpool in the area that we work. So that's why we're primarily using acoustics to understand this environment and to document where fish are in the water column. However, what that translates to is the fact that we have a lot of noise in our data. So what we get are these water column distributions that have to be interpreted to try to generate data that look like the bottom right-hand corner of this graph, which is hopefully what, when I say you, I'm saying actually industry and regulators want, maybe, to try to understand what is the encounter rate of fish with these devices. And then ultimately, hopefully getting to the point of, well, what would that impact be on the larger population? And this is not easy. Interpreting these results and getting the data so that we're certain enough to be able to provide these types of graphs has taken a long time for us, and there's still a lot of people scratching their heads on making sure that we're generating the right statistics for people to be thinking about how fish are using these areas and how they might be interacting with devices. So I wanted to kind of stop and take a reality check here to think about, what is all of what I just told you, how did that fit into the process that we've used over time in working with the industry and the regulators? Really, the reality check here is, I know we want to move to the point of talking about monitoring and having long-term assessment, or some kind of assessment that we can do that's kind of standard practice. But the reality is that this is an early industry, and the environments that these devices are going in are relatively unknown, and there is research involved with doing this work. So really considering the roles and perspectives of everybody who's involved in trying to move this industry forward is important. So from the regulator perspective, what laws apply? What questions need to be asked to address those laws? And really, how do we consider space and time issues to answer those questions? So from the scientific perspective, is a standard experimental method what we want to use? Can the questions that are being asked actually be answered, and what metrics should be applied? But really, I think from a scientific perspective, it's our job to provide the regulators and industry an unbiased piece of information to start answering these questions. And from an industry perspective, I really see, at least the work that we've done with ORPC, they've really provided a nexus for us to work together to try to answer some of these questions. So I come back to this diagram that I showed earlier. Really, all of this worked for ORPC because the scientists sat down with industry and the regulators early on and iteratively, continuously through this process to try to redefine needs and come back to the table to answer the right questions, to get a license essentially first, and then keep the industry moving forward. So the final thing that I kind of want to consider here are the importance of flexibility and communication. So as a scientist in this process, from my perspective, it's important for many scientists to maintain some consistency in the way they're approaching a question. But at the same time, the scientists need to be flexible. So from our perspective, we have a certain part of our study design that we've kept constant and consistent so that we can go back and ask our questions. How have things changed over time? But we've also built in some flexibility in the way that we're approaching the questions that we're asking, in terms of being able to be responsive to, for instance, the regulators. So some of the questions that you guys will be discussing later are, what is enough monitoring? And one of the things I wanted to bring up is that in Cobscook Bay, the regulators asked us, are the data that you are collecting after the first and second year going to be reflective of the entire bay? Our answer had to be no. And then we actually were able to find funding to help answer the question of how do we, can we get at that question? We actually conducted a study, and partway through that study, the regulators came to ORPC and they said, look, that's more than you need to do. Fortunately, we had separate funding to do that work, so we continued it, but in terms of the regulatory process, the regulators recognized when enough monitoring had occurred and where to draw the line. So I think that question needs to remain open. And from an industry perspective, what is enough monitoring? Hopefully you'll be working with regulators and scientists that can help through and find that point. And I think Carol talked about some of that earlier on. But really knowing about the system and the level of variability before you actually deploy is of great importance for understanding what will ultimately need to be monitored. And then, so I guess that's kind of my take-home message is flexibility and communication among everyone so that the industry can move forward. And I'll just end by saying, obviously, this work was done in partnership with a lot of people, most of which are listed here, and funding from various different sources. So now I hope you can undo my mute, because it's very disconcerting to sit in an empty room and know that there's a lot of people on the other side listening.
So Gail, you can hear me, right?
Yes.
Okay, great. So how about we've got time for just a few questions for Gail, and then we will have to break for lunch, but hopefully you might be able to hang on a little later on too. That's great.
Yeah.
Jocelyn?
Gail, it's Jocelyn. Thanks for that. I have a question about thinking about the fish that pass on the turbine. Just wondering if you could speak to the group about whether you're able to detect evasion at all, and whether you have any information about fates of those organisms.
Sorry, I kind of caught what you said. Were you asking?
I'm asking about that 48% of fish that you see that pass through the turbine, whether with your DIDSN technology you're able to collect any data about evasion or about fate of organisms, of those fish that pass through the turbine.
So the fish that pass through the turbine and we're able to see come out of on the other side, we can't, and what we couldn't do is link necessarily the fish that went in to the fish that came out, because there were two different cameras essentially. And so what we did see though on the departing side was a reorientation of fish. So we saw live fish coming through on the other side of all sizes, and they reoriented themselves into the current in the wake and then took off. So it's not clear from our work, and this is I would say a data gap. We were not able to see necessarily contact between a fish and a blade, because there's interference right at the blade, especially with the smaller sized fish that we were looking at. But I would say that what we saw on the far side of the device was quite interesting in terms of being able to see the fish reorient to the current and then continue on. But I could not tell you what % of the fish on the back side were the fish that we saw on the front side, so it's hard to make that calculation.
Okay. It's just a question about the active acoustics. Do you have any security that an active acoustic device itself does not change the behavior of the animals?
So, there's a lot of work going on that, fish or marine mammals in particular can avoid these active acoustic devices, obviously, depending on the frequency that they're operating in. The one that the DIDSNs are at very high frequencies, so they're, unlikely to be avoided necessarily, although the single beam acoustics that we've used have been at 38 and 200 kilohertz, which 200 kilohertz is just outside the hearing range of some of these animals, so it could be, and 38 is within the hearing range of some. Now, that said, we don't have the direct, any direct evidence that they're actually responding within, 2 hour active acoustics. So I've seen studies for example, clupeids and some of the, American shad, for example, can respond to 200 kilohertz active acoustics. But we have done like an anecdotal study where we have not seen shad respond. So it's kind of on the edge of what they may or may not respond to. So certainly you could potentially see responses to some of these devices.
Great, thanks.
Okay, I just have one last question, Gail, and that relates to the size of fish that you detected. From what I remember, they were actually quite small fish, and the size of fish, relative to the ORPC turbine and what they're likely to do and how they're likely to behave is a big factor. Can you just speak about that with regards to your project?
Yeah, so when I talked about fish size, and if we're talking specifically about the DIDSN work around the turbine, the fish that we saw in the study that I showed you the results for, most of the fish were actually 10 centimeters or less that we saw. Now, that's not to say that there aren't fish in Acoustic Bay that are bigger than that, and that's the point that I was trying to make when, the fish that passed by, most of them were also small, but there were some larger fish that went through there, and a lot of there's potential that the larger fish avoided at a greater distance, and we never even saw them. So you're pinning down a huge bay into a very small window.
Great, that's exactly what I wanted you to cover. Thanks a lot. Okay, Gail.
Thank you, Gail.
Thanks again, and thanks everybody for bearing with us with the technical issues.
So I'd say good afternoon Atlantic time, and good morning, not quite as early as it was in Seattle when the call started. Andrea asked me to talk a bit about integrated instrumentation for high flow sites. And this is going to be a combination of some slides that Andrea and I put together coming out of an instrumentation workshop that we held back in 2013. So Andrea gets co-credit or co-blame for this, depending on how you want to look at it. And melding that with some of the work that we've been doing here at UW on integrated instrumentation. So let's see, I think I can just hit this. There we go. Okay, so motivation for the talk. General motivation is that environmental studies at pilot projects that have been conducted to date have been expensive in relation to overall project costs. I think, as Gail, I think very really well put this, these early stage investigations have not been routine monitoring. They've really been R&D, trying to figure out methodology and produce results simultaneously. That's always expensive. But these have generally shown that small projects are unlikely to have biologically significant environmental impacts. And when I say impacts, I mean things that are really rising to the level of biological significance, perhaps at a population level. The problem has been that trying to extrapolate these results to larger commercial projects has been really difficult. So, going from, say, 1 tide gen to, 10 or 20 or 30 tide gen has been a real challenge. And one of this is that there's just been limited acceptance results that are able to reduce uncertainty for these larger commercial scale developments, which sets us up with this paradox for commercial scale marine renewable energy development. The paradox being that environmental monitoring costs are crippling to the industry if we take what we're doing now and just multiply by the number of devices going in the water. But if we have early commercial projects that actually do cause environmental harm because there were unanticipated impacts, that could cripple the industry. So we're left with a paradox of basically trying not to cripple the industry on either end as we think about how to proceed with environmental monitoring as we move out of kind of these one-off pilot projects and into commercial projects. I think Maygen being the first real example of this. So this is kind of a recap slide, early stage emphasis, near field, direct interactions with devices, distribution and use, so changes in habitat, and the effect of sound. I think you probably already covered most of this morning, so I'm not going to go into this in more detail unless Andrea stops me right now and says talk more about this.
Hey, Brian, you might say a quick bit about sound. We haven't actually.
Okay. So one of the concerns for early stage, one of the concerns that's kind of risen to the top of the queue in terms of things that we can actually study that we think might be significant is the production of underwater sound by tidal and wave converters. We're not worried about the sound causing acoustic injury the same way we do about, say, mid-frequency sonars or seismic exploration or pile driving, but we are concerned, because sound propagates so well in these environments, we are concerned about sound as kind of, I guess, the leading edge stressor that's likely to lead to avoidance. And so one of the things we are curious about is trying to understand the extent to which sound from these devices is likely to lead to behavioral changes at kind of the array scale and beyond. So next slide, we start thinking about the instruments that we can actually use to study these different interactions. Active acoustics certainly comes to the top of the list, and this is kind of summarizing some of the outcomes from this monitoring workshop. Gail certainly talked about active acoustics in more detail than I'm going to go into. She's also much more of an expert than I am. So some of the things that came out of the workshop was that active acoustics were, a great tool in terms of trying to make observations of what's going on around marine energy converters. They in general are not likely to cause behavioral disturbance, though that's obviously a question for the frequency involved. They produce data streams that in some cases can be analyzed in near real time, say for a multi-beam as for flowback. But is more complicated as you move up in resolution and go towards acoustic cameras. So some of the themes that kind of emerged from this instrumentation workshop were that deployment and survival at high flow sites was challenging for a lot of this instrumentation, especially if you're trying to do deployments that are not just a couple of weeks, but heading into months or even years. That direct interactions between a converter and marine animals was not currently observable with most active acoustic technologies. So Benjamin Williamson, who we've recently have just convinced to come to UW for a few months, coined this phrase, the last meter. The last meter is a real problem for active acoustics. You can't even if you are able to position cameras that are looking directly at, acoustic cameras looking directly at a device, there still is the problem of what happens right at the device. The acoustic return from the hard surface starts to obscure what's going on directly around the object. And the data processing and automation needs development. For the highest resolution active acoustics, high data intensity requires automated pre- or post-processing. I remember once asking Gail's graduate student Haley how long it took to process active acoustic data, and she said, well, for split beam it takes X amount of time, and for acoustic cameras it's as much time as you want to spend on it, which is not a good solution going forward. So we need better software tools here. And these data processing tools are not necessarily available for all types of active acoustics. So like I said, we've got good processing for split beam. We're getting much better processing for multi-beam. We're still working on the acoustic cameras to use them in a quantitative manner. Next tool that comes to mind is passive acoustics. This is primarily relevant to the study of sound, though we certainly can use this to try to look at distribution of use of vocalizing marine mammals. So the general consensus out of the instrumentation workshop is that hydrophones work well. There's several different types of hydrophones there shown on the right, everything from the kind of the smart hydrophone that Ocean Sonics has been producing that does onboard processing for streaming, to the Jasco AMAR, which is a relatively large capacity recording hydrophone, to CPODs, which I think Anna talked about a little this morning, a little hard to follow without actually being able to see what she was talking about. But a passive acoustic tool that's continuously monitoring but only intermittently recording based on kind of making an onboard call of what is likely to constitute a porpoise click. So the general feeling is that hydrophones are the right tool to study passive acoustics at these sites, but that there's room for improvement in high energy environments. And the big ones being flow noise for moored instrumentation at current sites, where the flow of water over the passive acoustic element is perceived as sound by the element itself. It's like the wind in your ears when you're riding a bike or someone blowing on a microphone, which I will not do right now. It's pseudo sound. It's sound that's not it's not true propagating sound, but it is, as far as the receiver is concerned, it can't discriminate between that and real sound. So trying to figure out ways to mitigate flow noise at high energy sites would be quite helpful. Also, there was a feeling that data processing and automation could use additional development. We have relatively high data intensity, especially as we go and start trying to collect information like porpoise echolocation. The data streams start to get up there. But the feeling was that with a small push, you could really move these to real-time processing. It was a much smaller bridge to, or much smaller gap to bridge than the situation for active acoustics. And then, so here's optical is obviously the other option, and this is kind of a video sequence that I like to show if, and I'm not sure if it's going to come through on that end, but it's a school of fish. This is 1 second of data, and if you look closely, there's actually a seal within that school of fish, and you can see two big eyes kind of staring back at you just to the left. I think I can annotate this a little bit. Just to the left of the frame here, that's a seal down in that school of fish. And so that's really the kind of the big benefit for optical. It has just unparalleled ability to give you resolution of what's going on in a given situation. But that unparalleled ability comes with a number of limitations. Optical systems don't have the same endurance as active acoustic. Optical systems are at depth, generally require some degree of artificial lighting, which is almost certainly going to influence behavior. It's a question to what extent it influences behavior. And the data streams that come out of optical systems are staggeringly large, even compared to active acoustic systems. So, a lot of power there, but also a lot of challenges. So when we think about what we're trying to do, the objective of any sort of early stage monitoring study is to try to reduce risk uncertainty. And if we kind of look at a spectrum of risk, which I know a number of you have seen this slide before, we have on one end discountable risks. And I'll use ORPC as another example, not because I'm trying to pick on ORPC, but because they've been a great company to work for and have provided a number of interesting kind of scenarios in this regard. One thing that was on the table early from regulators and fortunately got taken off was thermal monitoring. There was this concern, well, the turbine is extracting power from these natural environments. There's a wake. The wake mixes. That energy has to go somewhere. It goes to heat. So should we be worried about ORPC's turbines increasing the temperature of Cobscote Bay? No. We can say that really easily with pencil and paper calculation. It's a discountable risk. On the other end, we do have some risks that we know to be significant. And the really obvious one for this is we know that if a maintenance vessel is engaged in an operation around a TEC or a WEC, and it collides with something or runs aground and ruptures its fuel tank and spills fuel into the water, that's a real environmental impact. We know what that impact would be, and as a consequence, we put all sorts of basically procedures around to mitigate that risk and make that an extremely unlikely occurrence. The problem we currently face as an industry is between those are this regime of uncertain risks. And these uncertain risks are the ones that we're trying to monitor right now. And that's why we end up with these monitoring programs that have to try to address multiple risks because we have such broad uncertainty. So our goal should be to reduce uncertainty using these instruments and kind of focusing on these initial areas of interest. So one thing that's been talked about is to make a strategic research investment here to accomplish two things. One, and this is a phrase that I think I first heard from Nate at the instrumentation workshop, was this idea of retiring risk, taking risk that once we have sufficient data, we can basically provide enough data that regulators agree that this is a discountable risk, that it is a risk that we understand enough to responsibly retire it. So we're not talking about do monitoring at one site and draw conclusions that can be drawn to all. That's not something we should be doing as a science community, but we should be trying to provide data in a way that is comparable across sites so that regulators eventually can develop a balance of opinion on this to decide whether a risk is justifiably retired. Now, part of that monitoring will almost certainly increase the pool of significant risks that are actually identified and now require mitigation measures. But hopefully what we're going to find is this yellow bar of uncertain risks that we're monitoring right now, more of those apportioned to retirement than to identified risks. And obviously, as we scale up, we're always going to have residual uncertainty that we keep trying to drive down, but hopefully over time, we start to distill that uncertainty down a little bit more and really start to focus on a couple of things. So, the problem with doing this is that, in particular for severe outcomes, say collision risk, severe outcomes are likely to rarely occur. So if you want to try to observe those outcomes and they're going to be rare, then you're talking about trying to monitor interactions in a spatially comprehensive, so 360 coverage around, say, a device if you want to study collision, and temporally continuous monitoring. So this is 24/7 continuous monitoring and data collection. That would be the fastest way to make sure that you actually have observed all your possible severe outcomes and are not missing anything. The problem is, and this was a term that we started coining back at this 2013 workshop, is that this is a strategy likely to generate a data mortgage. And what I mean by data mortgage is best shown by an example here. So if you have a pair of stereo optical cameras, that's not going to give you even full coverage spatially. But let's say you're running 2 megapixel cameras at 10 frames per second. That's going to generate about 80 megabytes per second for the camera pair. If you do that for 3 months, that's 600 terabytes of raw storage. And obviously you can drive that down with video compression, but then there's the question of what you're losing by going to the compression. And if you were to then put out multiple pairs of cameras, you rapidly rise into kind of petabyte storage requirements. And that's well beyond the range of what most early stage developers can really hope to accomplish. And so this is kind of what when we mean data mortgage, we're not talking about a terabyte or two of data. We're talking about orders of magnitude more than that. We're talking about petabytes of data if we try to pursue this in a brute force manner. So when we think about how we might try to dig ourselves out of this hole, one silver bullet is to say, well, maybe we need instruments that only produce information. So they're not producing data. They're in real time sifting through everything and deciding exactly what we need to collect. And are just giving us the answer to our environmental questions. You can argue that some of the tracking tag information, like Anna was producing this morning, is getting kind of close to that when you're doing individual-based tracking. But I think we'd all agree, or hopefully we'd agree, that it's pretty close to science fiction for some of these things. So the pure hardware solution probably isn't going to work. On the other side, you could go with a pure software solution. So this would be the big data approach, where you basically just collect everything, you store it in these petabyte scale databases, you don't come into this with any sort of structured hypotheses, and you allow the data to define the hypotheses and then provide the information to you. That's kind of the bleeding edge of information science. I also consider that to be somewhat fancy in this situation, at least in relation to the sort of scale of resources we're likely to bring to bear on these early stage commercial projects. So what's the middle ground? Well, the feeling from the workshop participants was that integrated instrumentation packages were a potential way that at low cost we could develop near-term approaches that improve the ratio of information gained to data that we need to archive. And the way this might work, again, illustrated by example. So let's say we want to do detection, tracking, and identification of a marine mammal that's approaching a marine energy converter, a TEC or a WEC. So our kind of outer sphere for this might be passive acoustic detection. So this is a relatively mature technology. If we have a vocalizing marine mammal, for example, we can have coverage out to ranges on the order of 1 kilometer, and we're pretty close to being able to process that information coming in from the passive acoustics in real time. So let's say we actually do detect a marine mammal, and let's say it's within the sector of a multi-beam sonar that we have set up on the marine energy converter. Well, then the passive acoustic system could tell the multi-beam to switch on. The multi-beam could then start trying to track the marine mammal out to a range of about 100 meters. Again, with multi-beam, we're getting close to real-time tracking, so that can provide information to trigger another system. And maybe that other system is an optical camera at extremely short range where we're capturing just a small field of view, and it's going to almost certainly require archival processing, but we're only turning it on when we think there's good reason to believe that there's actually something to look at. So we're not just collecting a lot of blank information, we're really starting to target the really high bandwidth sensors at situations where we think there's a high probability of data to collect. The trick with this, when we start thinking about doing this in high flow environments, is we've got two basic constraints. One is if you're going to do a system like this, right now you really need a relatively high data and power bandwidth. You need to provide power to the instruments, and you need power to the computational resources to actually crunch the data that those instruments are collecting in near real time. That generally says that you need a cable. And cables that are not, so cables that are deployed in these high energy sites are subject to the same sort of loads as the instrumentation package, as the converters. Instrumentation cables end up looking pretty burly if you want to do this. And so that suggests that what we should be doing is trying to tie back into the existing export cables. So use the auxiliary power circuits in the export cables, use auxiliary communication circuits in the power export cables. We've had some bad experiences with trying to do this with analog communication or, say, DSL communication over copper. Better to do this over fiber. But what that does point to is you're going to use the marine energy converter's export cable. It means you need to be relatively closely coupled to the marine energy converter, which creates a paradox with your second constraint, is that because we're not actually sure exactly what we want to study at this point, and we're going to learn a lot through these initial studies, we need to be able to maintain the instrumentation, and we need to be able to adapt the instrumentation. So if we're maintaining and adapting, that says you need to be cabled, but you also need the package to be easily recoverable. And if you want to do that, that gets sort of difficult. And one approach that we've been thinking about at UW this is what we call a plug-in socket approach, where, I'll go to the next slide here, this is an example of a plug-in socket architecture. This is our adaptable monitoring package, the AMP. This is one of many different approaches that you could use to integrated monitoring, but it's the example that I know the most about, so it's the one I'm going to talk the most about. In the AMP style system, the plug is the AMP. That's what holds all the instrumentation, and the socket is what's holding the connection back to your power and data cable on the converter. It's mounted to the seafloor or to the converter itself, and that sits there for the duration of the project. It's the heavy fixed infrastructure, so you're only trying to recover and redeploy the AMP, but you're not messing with the actual cable connection on the seabed. So the reason that we've headed to this, and I'll explain that in another slide, but the kind of the AMP we're talking about, if you strip all the housing and cowling away, you end up with a kind of an integrated instrumentation package. So we've got optical systems that are illuminated by strobes. We've got Doppler profilers to measure current velocity. We've got acoustic cameras. We're trying to integrate a multi-beam under new work that'll start in January. We have all of the recovery and redeployment infrastructure there. We've got some legacy instruments. It's a pretty nice package, and it's starting to come together pretty nicely on the bench. And looking forward to taking it into the field soon. But there's a lot under the hood here for a system like that. Now, one of the things that we have under the hood here is this securement assembly. It's kind of in the middle of the amp, and that's a system that latches the amp onto a docking station. And that docking station contains one half of a wet-mate optical acoustic connector. So there's basically the plug on the amp. When the amp docks with that docking station, it latches on, and then an actuator drives this wet-mate connector into place. The wet-mate connector, both halves, are about $65,000. Which is courtesy of APL's discount from the Regional Scale Nodes project. If you were to buy this kind of off the shelf, it's about $100,000. So it's a pretty expensive piece of equipment. That's just the connector. But what that allows you to do is to basically mitigate risk in a number of other areas. So why did we decide to go with this, compact but relatively expensive option? Well, if you want to recover and redeploy instrumentation around a mech where it's closely coupled, one option is to use divers. I don't think divers are a particularly good idea because generally you have short work windows, and there's a significant human safety risk when you have divers in the water around a marine energy converter. So let's take that off the table. Second, potentially cheaper option is to just bring the converter back. If you're closely coupled to the converter, recover the converter and the instrumentation package, and do the maintenance cycle in parallel. That works if you need to do relatively frequent converter maintenance, but as we move forward as an industry, the idea should be to start getting to multi-year maintenance cycles, which is probably longer than the maintenance cycle you want on your oceanographic instrumentation, particularly if it's prototype instrumentation. Now, if you've got a WEC on the surface, I think this is actually a really good option. So if you have instrumentation that's on a WEC itself, just going out and doing the maintenance on the WEC makes a ton of sense. If you're trying to do maintenance around, say, an instrumentation package monitoring a WEC mooring or around a tech, converter recovery starts to look worse because bringing the entire converter back to the surface can be an expensive and risky operation. And so you're basically pushing off cost and risk on the instrumentation side onto the converter. So I don't think that's a great option either. Another option we really considered here for the amp specifically was a subsea winch. So the amp is basically on its socket, and when you want to bring it back to the surface, you unspool a subsea winch that allows the whole instrumentation package to come back to the surface, where it can be disconnected via a dry mate connector or maintained on the surface, and then the winch on the seabed engages once you're done and just ratchets the whole thing back down. The problem with the subsea winch approach is it has moving parts in the ocean, which is bad enough for the marine converter itself. But the big problem with the winch is that if you have a winch failure while you're midway through recovery or redeployment of the instrumentation package, that can lead to catastrophic system failure because now you have this unsecured package that's basically going to be subject to whatever wave loads and current loads are occurring once your maintenance window closes. So that's one way to get away from the wet mate connector, but it adds a huge amount of risk back into the system. And so another version that we thought about was ROV servicing. And this is what's done for regional scale nodes, which is the Ocean Observing Initiative project out on the west coast here of the U.S. The problem with ROV servicing, if you're trying to disconnect and reconnect individual instruments, is you have a short work window. So our approach to this is to use an ROV, a modified ROV, as an AMP deployment vehicle. So basically, we've called it a payload deployment system. And the idea here is that you lower the ROV and the AMP on a launch platform, shown on the right side there. You fly them towards this docking station. The ROV and tool skid position the AMP on the docking station, apply the actuation forces to clamp it on place and engage the wet mate connector, and then the ROV and tool skid disengage and go back to the surface and leave the AMP for its monitoring mission. So trying to do that turns out to be difficult because you're trying to design both the AMP to survive in high flow conditions and also an ROV that can operate and carry the AMP in high flow conditions. So this has turned into quite an engineering project of trying to do a combination of computational fluid dynamics, where we actually are simulating the drag forces on the ROV and the AMP to understand what sort of thrust requirements we need, and then starting to do tank testing as well. So on the right there, this is the initial tank testing of the Well, it's not what's going on here. I'm going to turn the sound off. I think it's trying to stream. Maybe I can't see it on my end, but maybe you're seeing it on your end. It's the ROV and Millennium Falcon basically operating in the tank and going through kind of just a standard turning operation. And what we've done here is we have this Millennium tool skid that contains 4 additional thrusters, which basically boosts the thrust output of a stock inspection class ROV, but still is able to use the exact same control architecture. So it's a cheap way to do that. So here's the summary here. We've got, my take is that integrated instrumentation packages are likely to play a critical role in reducing environmental risk without incurring large data mortgages, particularly in the near term. But that package design for these systems does require a significant engineering effort. It's not just about instrumentation and how to actually process the data. That's one project, but the other project is actually designing an engineering system that's actually viable for a high flow environment and can stand up to high flow environments. So with that, I'd like to acknowledge the support we've had from the Department of Energy and Snohomish PUD to develop the prototype system. We're certainly looking forward to continuing to work with Department of Energy on the development of integrated instrumentation, so basically developing what we call an intelligent amp or an IAMP that starts to integrate the output from all those individual sensors and actually use the amp in a targeted manner. We're also starting to work with Naval Facilities and Engineering Command on a Generation 2 amp, focusing more on the hardware and infrastructure side than the software side. So all that's a pretty exciting project, and these are pictures that just within the last week have been components coming out of the shops. On the left side is the prototype amp hull with some of the bottles installed on it. The middle shot is the prototype securement system that's going to go through force testing next week. And on the right side is the prototype docking station. And you can see the flange that the amp mounts to and clamps down. This has been a huge engineering effort on the part of myself, but mostly from a team that includes one of my grad students and then a huge group from the Applied Physics Lab at UW. So happy to take any questions, and hopefully, Andrea, that was about what you were looking for.
Perfect. Great, Brian. How about some questions? Nate Johnson is Environmental Director with ORPC, and he has been working with the company, and again, this is the turbine that Gail Zalewski was working around in Cobb's Bay. Go for it, Nate.
Thanks to Anna and Andrea for giving me the opportunity to participate in this. It's a great group. I think I've met many of you before, but to those who I haven't, it's a pleasure speaking over the phone, and hopefully everybody can hear me okay. So I'm going to try to be fairly brief and explain our experience with adaptive management and also what we've been doing lately that feeds into that process. 2014 has actually been a very busy year for us. We've had deployments on both coasts of North America, and also are heavily involved in what we call our technology optimization phase, which is the next version of our TIGEN unit that was installed in Cobb's Bay that Gail spoke about. So I'm going to speak a little bit about these projects briefly to give folks an idea of some of the environmental monitoring that's been going on with the projects and how that feeds into our adaptive management process, and then subsequently or conversely how the adaptive management process actually influences and impacts the status of the TIGEN being out of the water and how we proceed with that. So in addition to the TIGEN optimization, we've had a turbine installed, what we call a RibGen power system, in a river environment in the Quebec River in Alaska, and I'll talk a little bit about that, and also our OCGen power system, which is a floating tension link platform system that Gail alluded to as well, that I think Gail did a great job explaining a lot of elements of these projects. So let's see here. The TIGEN technology optimization, a lot of what I'll talk about in regards to adaptive management is framed around our Cobb's Bay project and our TIGEN technology. We first received a license from the Federal Energy Regulatory Commission here in the U.S., which is the federal agency with jurisdiction over hydrokinetic projects in 2012. And that same year we installed our TIGEN unit. We took it out of the water last year in 2013.
Hey Nate, your slides aren't advancing. Are you trying to advance them?
Yeah, mine shows that I'm on slide 3.
I think he's good now. He's good.
Okay, we're good. We're good. Thank you.
Okay. So you see slide 3.
Yes.
I'll back up just for a minute. Slide 2 is just an illustration of the different deployments we've had this year with RivGen in Alaska, OcGen in Acoustic Bay, which is actually at the mouth of the Bay of Fundy, and then our TiGen optimization phase, which is an engineering and design process out of our headquarters in Portland, primarily out of our headquarters in Portland. And again, the TiGen project is the one that we have a FERC license for. We are currently out of the water in the optimization phase, and that's actually taken a lot of collaboration with the adaptive management team to really figure out what the best process moving forward without a turbine in the water is, and modifying the levels of monitoring appropriately. And we've done that while the turbine was in the water as well. So this again is part of the FERC process, and I'm going to talk about that a little bit more a bit later. But that is what really established and coalesced the adaptive management team. And it's a license article of our FERC license to establish an adaptive management team. So and the other thing that we took advantage of with the turbine being out of the water this year and OcGen being in the water in the same site is we were able to do a benthic survey of the foundation that's still in place of the TiGen unit, which is really continuing to show an artificial reef development with really significant growth of blue mussels and sea urchins and starfish, both on the frame itself but also on the seabed, which Acoustic Bay is actually one of the heaviest dragged, commercially fished and dragged bays in Maine. And so with restrictions on that activity within our licensed site, that has contributed to the growth as well. So I'm going to move on to slide 4 here. So our OcGen module mooring project, Gail talked about this a bit. This is and this is a DOE-funded project in collaboration with the Maine Technology Institute as well. And this is taking our turbine technology and adding a buoyancy pod and tension leg platform system. So it no longer requires a fixed foundation like we did for the TiGen unit. It has 2 large gravity concrete and steel anchors, which are on the bottom left of this slide. The center picture on the bottom is what you saw from Gail, which actually is a Simrad image of the bottom support frame for the TiGen unit, as well as the floating OcGen. And then on the right is actually a minke whale that was at the site this summer in August, while the University of Maine was doing some of their fisheries monitoring. So there were a number of environmental monitoring aspects with this project. Gail did some terrific work under a separate DOE awarded project to do fisheries interaction monitoring around the device. We also did scour monitoring around the anchors, and it was really, as with RivGen, was an opportunity to really grow the knowledge base of environmental interactions with our power system, similar to RivGen. And the other note on the OcGen module mooring project, and this is something that we were very, very happy with. The permitting process actually was very, very efficient. And one of the things that made it efficient is it doesn't fall under the jurisdiction of FERC because it didn't produce power. It doesn't have a generator. It was meant primarily to test the mooring and anchoring system. And we worked with our adaptive management team from the Acoustic Bay site to really get their concurrence that this is an appropriate device as well as location to do the testing. We moved the location from another spot in Acoustic Bay to within our FERC license site for a number of reasons. We had a data cable already there and infrastructure. It also consolidated our activities in the bay, so there was less impact on the commercial fishing as well. So the process end to end, when we first started consulting the adaptive management team to the time that we had a permit to put this into the water, was about 6 months. And in fact, from the time we actually submitted the permit to when we received it was about 3 months. So, getting back to, I think Andrew made the comment that, the permitting in the U.S. has been very prohibitive. I think that is the case in a number of aspects and a number of projects, but as we continue to develop this relationship with our regulators around this site, it has become a much more efficient process. The regulators are very informed of the existing species in the bay by some of the work that Gail's been doing and others, and also very familiar with our power systems and what they entail. Excuse me, what the RPMs are, what the solidity is, how they perform, and I think that has led to a much more efficient process. And the Oxygen project was a good example of that. So this project is currently out of the water. And we felt it was an incredible success here this summer. And then, excuse me for a minute, our RibGen project was also a very successful project we had this summer in the river environment, the Kvichak River in Alaska. The Kvichak is one of the preeminent salmon runs in the world. So there's a real good opportunity to gather data and contribute to the knowledge base of power system interactions. There was a number of different environmental monitoring components on this project. The biological monitoring was done by a company called LGL. The University of Washington, Brian Pelagi, as well as Jim Thompson and a number of other folks did environmental monitoring as well. So the RibGen is a smaller version of our TiGen unit. It sits on two submersible pontoon structures. So the top picture you see there is actually the controlled descent of the RibGen. We submerged one side of the pontoons and then subsequently the other, and that was very successful. The LGL had outfitted one of the pontoons with 5 cameras and 2 sets of lights for optical monitoring of fisheries interactions. So there were 2 upstream cameras, 3 downstream cameras, and you can see on the lower left-hand corner that's actually the submerged system at night, or in low light. The center picture is actually a chum salmon in August that was captured on the foremost camera. They actually only captured fisheries interactions or appearances on the video from the foremost and the aftmost cameras. There weren't any appearances on the ones that were closest to the turbine itself. And the sample size was fairly low. This was in August. And but all the salmon observed, there was coho as well as pink salmon and chum salmon observed, really didn't get too close to the turbine and just took evasive action to avoid it. On the lower right hand is some of the University of Washington's work that they were doing around the turbine. They had what they call their DOPCATs, what are floating platforms for aqueducts to measure turbulence. They also measured wake and acoustic measurements off the RibGen as well. So, again, this is a real good opportunity for us to collect a lot of data. We plan on putting the RibGen back in the water next year, hopefully a little bit earlier in the season to capture the peak of the sockeye run, which will be really a good opportunity to get some data around a high number of fish. One of the things that we saw, and I think it's advantageous to interactions, is the way that the RibGen is sited in the Kvichak River contributes to the low number of interactions. It's in the thalweg, or the fastest moving part of the river. The salmon runs tend to be either closer to the surface if they're smolt, or on the edge of the banks of the river if they're returning adults. So that really minimizes the impact as well. So, moving on to slide 6. What do we know about project effects? We've had 3 different power systems in the water, and actually going back to our beta turbine that was installed off the barge, 4 different power systems. And we've been able to collect a lot of environmental data. And from that data that we've been able to collect to date, there's still certainly a lot of work to do, and Gail's assessing a lot of the data, and LGL's continuing to assess some of the fish data from Alaska. But what we are seeing in terms of impacts is positive impacts. So there's an obvious carbon offset when we're producing power to the bridge or to the grid, which we did in Acoustic Bay. We have not observed any environmental effects, negative environmental effects. No observed fish strikes or marine mammal strikes or evidence of barrier effects. We still see the fish passing by the turbine. Marine mammals as well, as evidenced by that minke whale that was at our site. And we certainly see the artificial reef development. That lower right-hand picture is the bottom support frame of TideGen about a year ago, actually, covered in blue mussels and starfish, and that growth has continued over time. So, knowing what we know, how do we move forward in the industry and try to keep the levels of monitoring proportional to what the actual risk is? And as we continue to develop this knowledge base, how do we quantify that risk, and how do we monitor for that accordingly? Right now in the industry, I think everybody's seeing in the industry, the amount of monitoring, both in terms of effort and cost, is really prohibitive. But we feel one of the key answers or key solutions to moving that forward is the adaptive management process. The adaptive management process is a way of really, it's a tool of trying to keep those levels of monitoring proportional to the risk as we continue to build that knowledge base. And ORPC has been very successful working with our adaptive management team. As I said, this was coalesced under our FERC license in the U.S., which was a license article to establish an adaptive management plan, as well as a team. And we meet typically biannually to review data and adjust levels of monitoring accordingly. And that process actually started very early on in the permitting process. I would say 5 or 6 years ago, when ORPC recognized the value of adaptive management, and also FERC established a MOU with the state of Maine that brought together all the agencies in one room to really move hydrokinetics forward. And that was kind of the beginning of the adaptive management team and the adaptive management process. So the folks that have been involved with it have been involved for a very long time. And it has been a very collaborative effort. It's building and maintaining trust from what we do, for being very open and honest. Understanding that the regulators have their own demands, and this is only a small component of what they're required to do on a daily basis. And then, really carrying through on commitments and giving the regulators the science-based data that they need to make decisions. They obviously have to adhere to their own strict mandates on protecting species, and so we need to give them the tools and the data that they need and can be comfortable in making good decisions on. So, we really, part of that is working with respected technical advisors like Gail and her team at University of Maine that bring not only innovative monitoring methodologies and technologies, but a level of independence to the table. We also have other technical advisors like Dr. Brandon Southall, who is a world-renowned acoustician and impacts on marine mammals. So having those people on our team, bringing that level of expertise to the table, and then working in a collaborative effort and bringing data from other projects. And it's, there was some discussion earlier today about, what the transferability of data gathered in other places is, and that's a very valid question. But state of the industry is we need to bring everything to the table we can, and then be able to make decisions based on that. So that's the framework that we've been working under for the Acoustic Bay project, and it's been very, very beneficial, I think, to everybody involved. I mentioned some of the demonstrated actions, but I'm going to go through this again, and on the right-hand side, there's also a list of the agencies, federal agencies that are involved in our adaptive management team. But this has been an evolving process from almost immediately after we received our FERC license to make modifications, and one of those first things you see is the removal of restrictive dates for pile driving. That was actually a restriction due to pile driving noise and Atlantic salmon smolt. We were able to demonstrate that the noise generated from pile driving in that first system did not exceed the thresholds that could induce damage in salmon smolt. So we were able to bring that data to the regulators and very early on in the process to make decisions to extend that window of our construction time to dry piles. And I mentioned the Octane project, and the Octane project is another huge step for us from a technology development standpoint, where we would be moving away from the fixed foundations to something that's more, which will further reduce some of the environmental costs and monitoring and impacts. Again, we've worked with the adaptive management team throughout the process, where we've developed annual reports, environmental reports for FERC, which they have reviewed and provided input on. We've met about the results before finalizing the reports, and made recommendations for modifications to monitoring as part of those reports as well. So we've reduced the frequency of benthic monitoring, reduced the frequency of scour monitoring. We've seceded we've halted the sea and shorebird monitoring as well. And those were all when we were still operating the Tidal device. Now that it's out of the water for technology enhancements, we've actually collaborated with the adaptive management team to proceed with what's called a temporary variance for many aspects of environmental monitoring while the device is out of the water. And again, I mentioned the collaborative effort related to Octane. And then finally, we just had a meeting with the adaptive management team about 2 weeks ago, and provided them with an update both on Octane, RivGen, the status of the technology upgrade, and then also about different permitting and licensing strategies moving forward. And it's really been a fabulous process. There's a level of comfort, a level of trust, and they really bring their expertise to the table to help us find appropriate ways to move forward with getting additional devices in the water. So finally, as we continue to build the knowledge base and continue to get a better understanding around environmental interactions with single devices, one of the real key things in the industry, and I heard folks mention this morning, is trying to get a grasp on how we move from single devices to commercial arrays. And that really is, on the forefront of, I think, of everybody's minds. And we are starting to do some research associated with that. Gail is involved with some projects with trying to determine what those mid-field and far-field effects are. And that really is going to contribute to the commercial array design. We're working with the national labs in the United States, like Sandia National Lab, who are doing hydraulic modeling that contribute to device array layouts and wake effects. So all those components are really starting to, as we get a better understanding of interactions around single devices, of trying to back up a little bit and see where the big issues are going to be as we get additional devices in the water, and there's other concerns. And as we move forward, we feel that the adaptive management process is really the key mechanism to continue to adjust those levels of monitoring as we go from single devices to more complicated, more diverse commercial arrays. And so it's been a very beneficial process for us now and in the past, but certainly it'll be even more vital to us and others in the industry as we do proceed with additional devices. So with that, hopefully I kept within the time frame. And again, I want to send my appreciation to everybody for being able to be involved in this workshop. It's certainly great to see some of the advancements in the industry, and I think there's going to be a lot more over the next couple of years. So, feel free to reach out to me anytime if there's any questions, and I'm certainly interested in participating in the rest of the workshop. Thank you.
Nate, thanks very much. That was great. Any direct questions for Nate? Sure. You're going to have to speak up a little more. They're hearing you from up here.
Okay. Just one question. You deployed the machine with the lights on at night time. Was there any evidence that attracted fish?
Nate, could you hear that?
All I heard was light. So if you could
repeat it. The question was,
if you deployed the RibGen device with lights on at night, how did this affect the behavior of the fish?
Whether or not that attracted fish.
Yeah, did it attract fish? And did you think you saw more, less?
Yeah, no, that's a great question, and there's been, Brian alluded to it earlier as well. There's been a lot of discussion about that. So to clarify, on the RibGen project, ORPC has led a lot of the permitting efforts. For RibGen, we were solely a device supplier, so we did not lead the permitting effort and did not design that monitoring plan for the Quebec River. So, I think that the number of video observations during night time was either very few or none. So it's tough to say what the actual impact of the lights, but we certainly are in agreement with what Brian said earlier, that it certainly would have an impact on behavior around the device. So for example, our Acoustic-based project does not have lights in it, and that is something that we will certainly probably revisit as we put the RibGen back into the water next year, and actually we're taking a larger role next year in the permitting effort, so that's something that we'll certainly revisit. So I don't think there's any quantitative results in terms of what the impact of the lights may or may not have been, but we do anticipate there would be probably some behavioral changes.
And Nate, this is Brian. If I can just add one thing to that, I think the question of behavioral changes from the light is probably somewhat mitigated in the river environment where you have continuous flows, and certainly operating on the river, 2.5 meters per second doesn't sound like a lot, but when you're operating out there, you pass by the turbine in a blink if you're drifting with the current. And the light doesn't penetrate that far. So I think that you can almost think of the continuous lighting there as being the equivalent of almost an extremely intermittent strobe in a lower flow environment where fish can basically freely approach the structure rather than having to fight the current to do so.